Hello, colleagues. Hello, everyone. Good morning and good evening. Today we have a very important webinar. It is very essential to understanding how to estimate the evapotranspiration, which is very important for every crop. Today we listen to Dr. Professor Rajab, who is a distinguished figure. Will explain to us the results of EU-funded project, which uses new technologies to estimate the actual evapotranspiration and compared with actual measurements. Professor Rajab is a fellow principal hydrologist and water resources management specialist, honorary president of the International Commission on Irrigation and Drainage, ICID, which is famous, adjunct professor in Alexandria University, editor Cambridge University. And actually, he held many positions, and it will take time to explain all his professional positions in different countries. So I prefer to keep him, allow him to start the webinar, and maybe would like to define himself more better than me. So I will stop share. And please, Rajab, share your screen.
Thank you, Dr. Abdelazim, and thank you for inviting me for this webinar. Let me share my screen. Hello, everyone, and good evening or good morning. I'm really quite happy to talk to you about one of the very important subjects really for irrigation. And this is about new technologies that we used to try to estimate the crop water requirements. And I will get through what we did in one of the EU-funded projects, in addition to others as well. Water for irrigation. Irrigation actually consumes about 70% of the global freshwater resources. In some countries, it actually consumes more than 70%. Some countries consume 85% or more of their freshwater resources for irrigation. So it is really important to quantify and to save water for irrigation. We are facing so many challenges. By 2050, the world population is expected to increase to 9.8 billion. And that actually requires that the food demand is expected to increase by 100%, and that requires more irrigation water. And freshwater resources are really very limited. Second challenge, that water consumption is expected to increase by 50%, and our water resources are limited. Increase in global energy demand by 30 to 40%, and irrigation requires energy. Currently, there is an increasing gap between water supply and demand, and by 2030, a 40% overall gap between global water supply and demand is expected. Climate change predicted increase vulnerability of agricultural sector, especially in developing countries and in the Mediterranean region in particular. So the water availability for irrigation brings us to two questions. Do we have sufficient water resources for irrigation? The second question, do we have sustainable management of water resources for irrigation? Looking at some work we did in different parts of the world, I'll just give a few examples. A work we did in Cyprus Island, we found by 2050, the gap between water supply and demand is increasing by the time. And given the water resources ministry in Nicosia were part of that project, they were actually taking decisions to limit the areas of surface irrigation. A work also in south of Italy catchments also indicated that there is also a gap between water supply and demand, and that gap is increasing by the time. And that's also a warning sign that we should save more water. Another two catchments in Brazil, in northeast of Brazil, work in area of Fortaleza or Recife, which is a semi-arid part of Brazil, indicates there is a reduction in the groundwater recharge and the surface water by the time, and that actually alarming sign that we should save more water. The work we did recently on 7 catchments in the UK, starting from the north of the UK and Scotland to Midlands to Cornwall, and in the south, we had 7 catchments. Was a project funded by the British government, and all those 7 catchments, that 6 of them showed us a future gap also between water supply and demand, as you see here on that catchment. This is one of them, but that's the Don catchment in Midlands near Sheffield and area, and that's actually another alarming, even for a humid country like the UK. So the rationale behind really the crop water requirements issue is that the accurate estimation of irrigation water requirement is necessary and to minimize the losses and to allow more land to be irrigated and subsequently more food to be produced. Also, we need to double our food by 2050 to feed 9.8 billion inhabitants, while the water resources supplies are very limited. Irrigation practitioners have always faced the challenge of when to irrigate and how much water to apply. To answer those questions, several methods have been developed, but the accuracy of all those methods and the scale they represent are of great importance. The unanswered question, when to irrigate and how much water to apply. This is the question. Who should answer? The crop, the soil, the weather, or the atmosphere? Call a friend or ask Dr. Google. Most people do ask Google. The crop water requirements determination, we had several ways of doing it in the past. Equations based on hydrological data, temperature, energy, or energy and combination, empirical equations, soil measurements like soil moisture content, soil moisture deficit, zero flux plane, moisture profiles, soil water balance, plant measurements like sap flow, mostly for orchards, canopy temperature, or the difference between the canopy and atmosphere temperatures, lysimeters, weighing and non-weighing lysimeters, measurements, direct and indirect, like class A pan, scintillometer, Eddy Covariance, bound ratio. Why we need an accurate estimation of crop water requirements? The accurate estimate of crop water requirements has impact as adding more water, you add more salts if you are irrigating with saline water. Adding more water, it means you do more leaching of the nutrients and fertilizers. Adding more water, you decrease soil and the groundwater qualities. Add more water, decreasing water productivity and water use efficiency. Adding more water, you irrigate less area, wasting water resources, labor and energy and money, increasing the range water volume as well. So before I go into the evapotranspiration estimation, let us have these definitions in mind. We have the reference evapotranspiration, the crop evapotranspiration, and the actual evapotranspiration. The reference evapotranspiration has been defined as the rate at which water, if readily available, would be removed from the soil and plant surface. And that reference crop could be alfalfa or grass. The ATC is the potential evapotranspiration for a cropped area. It is quantified through the multiplication of ET node with crop coefficient Kc, which is another problem. In agriculture, ATC is the maximum possible evapotranspiration rate under the prevailing meteorological conditions under unlimited water availability. And that's the point that a lot of people don't really take that into consideration. ETA is the actual evapotranspiration of the amount of water that's available under the actual level of soil moisture, not the amount of water that can be evaporated if the soil contains an unlimited amount of available water. How we started? We started in the early days by evaporation class A pan, which is a free surface water, and the evaporation has no control by the plant. It means no biological control whatsoever. And that technology was followed by looking at class A pan factor in order to reduce the amount of evaporation to bring it to the level of the crop or biological controlled evaporation. Then with the development of weather stations, we started to see more equations based on temperature or energy or combination of the energy and temperature. Some of these equations were empirical and some of these equations were site specific. Until 1965, it was the first attempt by Penman-Monteith. These two British scientists developed an equation for the first time to account for the presence of plant. And they represented the plant by that term, RS, or stomata conductance, or stomata resistance. And that was the first equation that really considered the plant. Other equations were developed by meteorologists, and they didn't really consider the plants at all. And it was really missing one of the vital parameters that represents the crops. So this is the first equation that the plant or the crop was recognized as important factor in the calculation of evapotranspiration. However, the conductance or stomata resistance changes over the day in 24 hours, being at its lowest level at the night time or early of the day, and then maximum at the midday or noon. And also it varies with time during the season. Here is the season from May to October. And you can see here the stomata is changing from the beginning of the season to the end of the season. And this stomata conductance and resistance varies during the day and also during the season. That actually made it difficult for some academics and practitioners to apply the original Penman-Monteith equation. Then FAO and ICID, they got together and they started to look of ways to simplify that parameter in order for people to use that equation and still has some representation of the crop. So they assumed the conductance or stomata conductance or the resistance to be represented by an average seasonal value of 70 seconds per meter. So that was a flat, straight line, horizontal line, and instead of the sine wave function as we see in nature. So this is the natural way of the stomata conductance or resistance. And the FAO and ICID, they came with one fixed value all over the season, and that's 70 seconds per meter, to put it into the Penman-Monteith original equation and to simplify equation so people can use it. And they came with this equation. Here you won't see any more RS, or the stomata conductance or the resistance. So here you calculate the AT node with the reference evapotranspiration, and then multiply it by the Kc, which is a combination of two crop coefficients. One is related to the crop, one is related to the soil. And that's really the modification of that equation. However, some scientists, they started to test this equation and to start to check if this equation and the simplification is really correct, or it is overestimating or underestimating the real evapotranspiration. In EU-funded project, Water for Crops, that project was funded by European Commission. It had actually 36 organizations, 14 from India and 22 from Europe. And it has been a well-funded project. And we started to look for sites where we can check on this equation, and also to apply new technology and to see how can we measure the evapotranspiration and accurately calculate the crop water requirements. So this is a site here in Bologna, north of Italy, with our Italian collaborators. We started to work together on that site. I would like to acknowledge the contributions and for the work done by my colleagues, Jonathan Evans from UK Center for Ecology and Hydrology, and Adriano Batalani and Dominic Solimando from Italy. So we work together on that site, and we instrumented the site, and we got the results that I'm about to show. So the site, in terms of soil, it is highly silty soil with fine sand. Crop rotation is typical, triennial, or including sequence of cereals and horticulture crops. And the irrigation is sprinkler and the drip. The equipments that we used on that site is the Eddy Covariance and Scintillometer and the Cosmos. And the location of the site here, you have the Cosmos and the Covariance at that point, Scintillometer receiver and Scintillometer transmitter here. So we have that transect. I will start by Eddy Covariance. The Eddy Covariance is a direct method of measuring actual evapotranspiration. In this technique, fast fluctuations of vertical wind speed are correlated with the fast fluctuations in atmospheric water vapor density. This method directly estimates the transfer of water or vapor or evapotranspiration from the land or a canopy surface to the atmosphere. The Eddy Covariance approach is considered to be a direct and accurate method to measure both the latent heat, which is evaporation, and sensible heat fluxes. This instrument is commonly used for greenhouse gas emission, carbon dioxide and methane emission monitoring, measuring water loss by evapotranspiration, and there is nowadays a novel use that includes carbon sequestration, capturing, monitoring, measuring landfill gas emission, and atmosphere gas leak detection and the location, and the methane emission from hydrolyzed fields. Now, the Eddy Covariance method is one of the most accurate direct approach that we saw when it comes to gas fluxes. And it can actually use direct measurements of evaporation, sensible heat flux, CO2 flux. The method relies on direct and very fast measurements of actual gas transport by the 3D wind speed in the real time in situ, resulting calculations of turbulent fluxes within atmospheric boundary layer. And this is really how it looks like in nature. And those sensors here that you see in the picture, in between those sensors, if I can go back, those sensors here, when the flux goes in between, horizontal flux, they measure the evapotranspiration. And that's actually horizontal flux is eddies, and those eddies, they move with direction of the wind, and we can calculate the change actually here in the airflow within those sensors. The scintillometers, slightly different. It is a beam transmitted from the transmitter and detected at the other end by a receiver. So it transmits near infrared light from its transmitter, and its receiver measures the fluctuation of the beam radius. This beam fluctuates are caused by inhomogeneity of refractive index along the optical path. This technique, where the scintillation of a transmitted optical or radio wave signal in conjunction with standard meteorological measurements, is used to calculate the sensible heat flux. Latent heat flux is more commonly calculated as residual of the energy balance. However, there are some scientists managed to get the latent heat also obtained from scintillometers with the knowledge of the water balance. A scintillometer consists of transmitter and the receiver, where an optical or radio wave signal is transmitted to receiver across paths, sometimes over a few kilometers. The signal transmitted is usually scattered by turbulent atmosphere. The sensed intensity fluctuations or scintillations of the signals are analyzed at the receiver and expressed as a refractive index of the air. So this is here how it looks like. So here is the transmitter and here is the receiver, and this can go up to 10 kilometers. We tried that actually in Crete Island, and we used 6 kilometers to calculate the evapotranspiration over the Crete Island. So we have here the transmitter, and then you have here the change in air density under the beam, and that change of air density is related to the change in temperature and the change in relative humidity. So the refractive index changes is because of the air density differences caused by the heat and relative humidity and or moisture. Scintillometry uses these changes in the refractive index of air to derive surface fluxes. The applications we had before, and my colleague, Jonathan Evans, tried that on area of 2.4 kilometers in southeast of the UK, in Berkshire. And he found, when compared with the Eddy Covariance, there is a good agreement between the two. The scintillometer was also used by other scientists, and also they found that the scintillometry technology can be used to estimate ET at scale of several kilometers. A study at Logan Dam, also they have been able to find that ET over the dam, when compared with the Eddy Covariance placed at the center of the dam, they also match each other. In a field experiment in central region of Morocco on orchards, also they found that the scintillometers can be a potential device to provide an estimate of large evapotranspiration. But so far, there's very little about the scintillometer application in agricultural land or in conjunction with irrigation crop water requirement. So here we tried to do that. So here we put here the transmitter and the receiver, and we started to look at the footprint of the evapotranspiration measured by the scintillometer and the Eddy Covariance. And we take into account the prevailing wind direction when we calculate actually the evapotranspiration. And then we can also split the total evapotranspiration obtained by Eddy Covariance and scintillometers into a different contribution of different crops. For example, this is here in this figure, we can see the wheat contributed 44% of the total evaporation measured by scintillometer and Eddy Covariance, and maize field contributed 35%, tomato contributed 4%, and the other crops contributed 17%. So we can break it down to which crop contributed how much. And that's brought us to comparing the evapotranspiration that we obtained by the Eddy Covariance and scintillometer with the reference evapotranspiration calculated by Penman-Monteith equation modified by FAO and ICID in 1998. So in this graph, the continuous gray line here, this is the reference evapotranspiration, that's continuous line. And then we compare that with what we measured by as actual evapotranspiration by scintillometers and Eddy Covariance. The Eddy Covariance is the blue dots here, and the scintillometer is the orange dots, well below, of course, the 80 reference obtained by the equation. Then if we multiply the 80 reference obtained by FAO modified equation by the KC here is a weighted mean of the KC of other crops. Then we obtain the yellow dots, which is the ATC or crop evapotranspiration. Still, you can see that the scintillometers and Eddy Covariance evapotranspiration actual is well below the crop evapotranspiration calculated by the equation. If we make a ratio of the total evapotranspiration of the season, then we can see per season the ATA obtained by Eddy Covariance compared to the AT node is about 44%, and the ATA obtained by scintillometer about 35% of the AT node. And when we compare that, the total evaporation of the season obtained by the Eddy Covariance, it is about 45% of what's calculated by the modified Penman-Monteith equation. And when we look at the scintillometers values, they are really 35% when compared to the ATC obtained by the modified Penman-Monteith equation. So that's actually quite a big difference between the actual evapotranspiration measured directly by the Eddy Covariance and scintillometer was that calculated by the modified Penman-Monteith. So the Penman-Monteith equation showed higher values than those obtained by Eddy Covariance and scintillometer. And we could see there is 45%, 35% of these values. And that brings us to another issue. A lot of researchers reported that the obtained yield at 50 or 60 or 70% of the full crop water requirements calculated by the modified Penman-Monteith, the same yield as if when they apply 100% irrigation water. So how can you obtain the same yield when you apply half of the water, the same as if you apply the whole water amount? And that's what's so-called by some scientists deficit irrigation. Is it really deficit? That's the question. Is it really deficit or just it is actual requirement? And the full irrigation requirement was exaggerated due to the overestimation by the method used to determine the crop water requirement. And I refer to that in a paper recently published under misconceptions and misunderstanding in agricultural water management, time for revisiting, reflection, and rethinking. That paper has got about 10 issues. Deficit irrigation misunderstanding is one of them. So I would encourage those interested to have a look at the paper. Some additional remarks: calculating reference evapotranspiration, ET node, or the crop evapotranspiration, ETC, from meteorological data produces potential evapotranspiration that would represent the atmospheric demand for water rather than the crop demand for water, because it's simply based on weather data, hardly crop data. The accurate crop water requirement should be based on crop demand rather than the atmospheric demand for water. And that's really the principle we should stick to. Another benefit is this modern technology of measuring the actual evapotranspiration do not need crop coefficient, as obtaining KC is a major problem to many irrigation practitioners. Other methods for measuring actual evapotranspiration can also be useful. For example, weighing lysimeter. But be aware, the scale is too small. If Eddy Covariance or scintillometers are not available or not affordable, it's not the end of the world. There is always way out of that. Short-term monitoring of actual evaporation using any method could be used to derive a relationship between what's commonly used as ET node or ATP that are easily obtainable from standard weather stations. You can simply calculate your ET node or ATP, but do, in addition to that, a short-term experiment and to try to find a relationship between what you really measured actually in that short-term experiment and what you obtain from the calculations of your equations that based on weather data, and try to find out a correction or a relationship. Some supporting findings that I found, I wasn't the only one who found that the evapotranspiration by the modified Penman-Monteith overestimates the evapotranspiration. Here, other scientists used lysimeters, and also they found that the equation calculated the high ET node and the high KC, which led to a higher estimation of crop water requirement of potato crop in India. Another researcher in Jordan Valley, they also used the AC or Eddy Covariance, and they found actually is 36% less the evaporation obtained by Eddy Covariance than those reported by FAO. And in Portugal as well, they have also used the AC or Eddy Covariance, and they found there is overestimation by the equation of FAO compared with what they measured by Eddy Covariance. So there are several, I just selected a few here, and that shows us that we've got to be careful with what instruments that we use in terms of measuring evapotranspiration. The next subject is estimating crop water requirements using a soil moisture observations. Why is the soil moisture important? Soil moisture controls hydrological processes such as runoff, infiltration, recharge to the groundwater, evaporation, availability of water to plants or the crops, and available water resources. How we started measuring the soil moisture? We started by soil cores, like everyone else. Then we move to neutron probe. But because you have here that label of radioactive sign, the Environment Agency in the UK prevented us from using it, and they were discouraging us from taking it unless we have on the Land Rover that label, and we have to train people how to hold the neutron probe so the radioactive should be away from their bodies. So with some health and safety issues with the use of neutron probe. So Delta T company in Cambridge, they came with an idea similar to neutron probe. It's called profile probe, where you can measure the soil moisture at different depths without having a radioactive source. But this is still a point measurement. This is also point measurement. This is also point measurements. It doesn't give you an area-based measurements. So we started to look at other technologies. One of them is ERT, electric resistivity tomography, which is a transect from one end to the other end. That transect is about 32 meters each. And we could use that to monitor the soil moisture along the transect. And with the remote sensing images, we started to do transects, and we started to do either ERT or something else is called skip, which is something you push into the soil at 5 or 10 centimeters, and then we calculate the soil moisture as we go on to try to calibrate the images coming from remote sensing. But that was a hard work. So we started to pay more attention to ERT and to try to develop this method, which is really to use a current from the back of the car here. So from a battery, and we apply a current, and we look at the resistivity to the current based on the soil moisture. More water, less resistance. Less water, more resistance. As simple as that. And we started to look at the soil moisture under the transect. That transect can be 32 meters or multiplication of 32 meters. We might need additional battery. And we look at the changes in soil moisture content. And this is really how we do it in the field. Just you take the car and the batteries inside, and you apply that, and you can get a good image of really what's happening here. Also under different vegetation, as the water uptake by different vegetations differ, and then you can really see how different vegetation, especially during the drought periods, which vegetation survives better than the other. And also you can identify the soils, which soils in the drought can supply water better than the others. And we discovered the chalk soils in the UK can supply water longer than the clay soils when you have a drought period. We also, in Water for Crops project, use the transects or ART to look at the distribution efficiency of the drip irrigation, here regulated drip irrigation system, and this one under PRD, partial root drying method, to look at how homogeneous the drip water was distributed in the system. So estimating the crop water requirements using the Cosmos soil moisture observation system came after we started to pay more attention to area-based. We wanted to move away from the point-based measurements or transect-based measurements to an area-based, something to a larger scale. So that brings us to who actually discovered the Cosmos system. The Cosmos rays was discovered by a German scientist in 1912. In 1912, he wrote in his book, Vector His, I was able to demonstrate by means of balloon ascents that ionization increased from 1,000 meters and at 5 kilometers reached several times the value at the Earth level. I concluded that this ionization might be attributed to the penetration of the Earth's atmosphere from outer space by unknown radiation of exceptionally high penetrating capacity, which was still able to ionize the air at the Earth's surface. To clarify the origin of this radiation, I undertook a balloon ascent at a time of nearly complete solar eclipse on the 12th of April 1912, and took measurements at heights of 2 to 3 kilometers that I was able to observe no radiation in ionization during the eclipse. I decided that the sun could not be the source of cosmic rays. So that's the conclusion of Victor Hess. He discovered there is high penetrating radiation coming from outer space, but he doubted, is it the sun? And then when he went with his hot air balloon to up to 5 kilometers on eclipse day, no sun, sun was not out, he discovered actually the ionization was happening in absence of the sun. So this sort of radiation is coming from the outer space. So the cosmic ray observation system principles are: the cosmic ray was discovered by Victor Hess. Fast neutrons are generated naturally at the land surface by energetic cosmic rays. These background neutrons respond strongly to the presence of water at or near the land surface. These ambient neutrons are generated primarily by interactions of secondary cosmic rays neutrons with terrestrial and atmospheric nuclei. So the cosmos, or the cosmic rays, when actually it comes from outer space, it interacts with the biosphere, which is the area above the soil surface. And that interaction between the biosphere and the outer space, high penetrating, high energy radiation of cosmos, generates neutrons. Those neutrons, they have the same atomic weight of hydrogen. And when they collide with the hydrogen, they lose some of their velocity. And we can count down how many of those neutrons became slower and how many still are fast neutrons. And this is the same principle as neutron probe, if you remember. So the conventional method of measuring soil moisture generally provide either a point source or soil profile data at specific point. Alternative methods of new technology are now available, which make use of indirect sensing technologies to produce area-based integrated soil moisture. Soil moisture at horizontal scale of 300 to 700 meter diameter and depth of 12 to 70 centimeters can be inferred from measurements of naturally occurring cosmic ray neutrons that are moderated mainly by the hydrogen atoms in the water backscattered to the atmosphere. The count of the resulting slow neutrons above the ground is sensitive to water content, largely insensitive to soil chemistry, and inversely correlated with hydrogen content of the soil water. An integrated measurements of the average count over a few hours is made by a neutron detector placed above the ground, known as Cosmos Ray Sensor. And that's the CR, or the CR tube. So the high energy neutrons from cosmic rays are slowed and partly absorbed by the hydrogen atoms in soil water. Some lower energy fast neutrons are scattered back from the soil. The CRS, the vertical tube in the photo here, continuously counts these fast neutrons. As soil moisture increases, fewer fast neutrons escape from the soil, and therefore count rate reduces. The cosmos moisture is a large scale measurements as 300 to 700 meter radius of sensitivity. Non-invasive, completely passive. Use background fast neutrons generated by cosmic rays, which are scattered, slowed by H, or hydrogen atoms. Gives a more representative soil moisture based on area, not on a single point. Could help to obtain the soil moisture deficit, to estimate irrigation water requirement from more area representative integrated soil moisture, and avoiding the point scale measurements or heterogeneity. Soil moisture for us here in the UK, where actually our irrigation, mostly supplementary irrigation, and our agriculture here is more rain-fed agriculture. But the soil moisture for us here in the UK is important for other things like surface runoff generation. So we use the cosmos here for so many things about drought monitoring, climate science, weather forecasting, ecological status, land atmosphere processes, groundwater recharge. So we use the cosmos not only for irrigation, but for so many things. Irrigation is not practiced as in other countries here in the UK, but it is used for flood predictions. If your surface, soil surface layer is saturated, it's very likely if you have a rainfall event expected, you are highly likely to get a runoff. And if you are a reservoir manager, then you have to pay attention that either you release some of your water through the spillway to account for the oncoming runoff, or if you are a farmer, then you could maybe delay the sowing date and your farming activities until the runoff is over. So there's different applications for the cosmos soil moisture measurements. And here in the UK, we have about 52, if not more by now, stations for cosmos. And also in agreement with China and India, we have now several cosmos stations across India, China, and currently there is also some stations are in Africa, and there is now more work going on across Africa in particular. And there is a website for all the data that comes from Cosmos measurements that goes into that website live in real time. And you can actually look at the location, and then you can have a look at the soil moisture of that location in real time. So, however, when we started to use the Cosmos in Water for Crops project in that site in Bologna, I was looking at the application in terms of agriculture, in terms of agricultural water management, in terms of irrigation. So that's different application from what we used to have in the UK. So I needed to do two things. One is to see the effective depth of Cosmos for agriculture irrigated areas. And number two, I needed also to know how far the Cosmos can sense the soil moisture from the tube. Is it 100 meters, 200 meters away? I can get the measurements and for how deep. So that were two questions. And for that reason, I started to do the calibration of the Cosmos in irrigated agricultural lands in Bologna. So for that reason, I started to use profile probes measurements to compare it with the Cosmos at different depths. I also used soil cores. I also used soil sensors, soil moisture sensors. And that's the map of the calibration. Here is the Cosmos tube, and this is about 100-meter distance across the field, different fields and different crops. And here we have the profile probes, and we have the soil moisture sensors, and we have the soil cores locations, and we started to look at the comparison between what we obtain from these measurements and what we obtain from the cosmos. We also used the salt med model, which I developed some years ago, and it's still available and in use. It is available on ICID website. It's a free download. You can download it. And that's for field scale measurements. And we use that to generate daily values of biomass and also daily values of soil moisture to compare it with the cosmos. There are some publications about salt med model if you want to read more. There are 3 special issues about it. But also we calculated the soil moisture deficit based on the soil moisture obtained from the cosmos and also to try to classify the level of soil moisture deficit as you will see in the figure. So that's really the figure that we obtained from using the cosmos. So here is the soil moisture content of the cosmos. This is the rainfall, and you can see here when you have rainfall, the cosmos is very sensitive and it goes up straight away the soil moisture. So it's very sensitive device to detect if you see here that rainfall straight shoots up. And we use these soil moisture values to calculate the soil moisture deficit. And based on the FAO classification of the different levels of stress, depending on the soil moisture deficit values, we color-coded the soil moisture deficit stress to red, which means that highly stressed and you need to irrigate. Green, it means low stress, you don't need to irrigate. Amber, here, like yellow, mild stress. So you could actually, from that, you can use the cosmos as operational system. It's real-time measurements. Once you do the software to calculate your SMD, and then you put the levels, you can trigger the irrigation system when it comes to the orange or the red. So your irrigation system starts to irrigate and to stop at the level when you reach to the green level, which is something that can be operational. We didn't do that because in the UK we don't, as I mentioned, we are not concerned about irrigation much, but I hope that sometime we'll be able to bring this into operational level and to make a good use of this technology. When we compare the soil moisture of the cosmos with the profile probes and sensors and soil cores, and we found actually the root mean square error was very low. So it was really a good agreement between the soil moisture measurements obtained by the cosmos and by the cores, soil profile, and the sensors. So in summary, the above results show that the cosmos soil moisture falls within the band of the top 0 to 60 centimeter layer soil moisture measured by sensors, soil cores, and profile probes. So that's what we found. The measurements of soil moisture from 0 to 60 centimeters was matching the one obtained by the cosmos. This could indicate that there is a possibility that the cosmos probe effective depths could be within the top 0.60 centimeter of the irrigated land, particularly during the summer crop season. In such a case, knowing that almost 80% of the crop root system is accommodated within the top 60 centimeter, cosmos measurements could be useful for monitoring the soil water status and subsequently soil moisture deficit in the root zone. A soil moisture deficit is also used as an indicator for irrigation water need. The crop irrigation requirement could also be based on the soil moisture deficit of the root zone or the top 0 to 6 centimeters of soil when measured by cosmos probes. As for the horizontal extent of sensing, the current study shows that the soil moisture measured by profile probes at a distance of 100 meters away from the CRS tube is close to those measured by Cosmos. Given there were no further access tubes beyond 100 meters, it is possible that the Cosmos is able to sense larger horizontal extent beyond 100 meters as reported by other scientists. And there are some applications by others here use the Cosmos rays, and they used it in combination with satellite remote sensing, and also they found it's very useful to calibrate the images. When it comes to the Cosmos effective depth and distance verification, there were some papers here indicated the effective depths could be from 12 to 70 centimeters and from 15 to 80 centimeters in another publications. And when it is related to how far the Cosmos can sense, then there is here publications. Some people, they found it from 130 to 240. In the UK, they use up to 60 meters distance of sensing for Cosmos. Here are some publications. I put them in the chat box. I hope you will be able to get them. If not, I'll try again. And once these actually, the Cosmos and Scintillometer research papers appeared, Wiley issued press release about these publications. So they were quite happy to see something new or new directions for applications of Scintillometer, Eddy Covariance, and Cosmos. So the accurate crop water requirement should really not be standalone. It should be combined with efficient irrigation system and the network together to be the way forward. So you cannot really only look at accurate water requirement and not to use efficient irrigation system. So we have to think more integrated way. And if now we go back to the early civilization started beside rivers, like Egyptian early civilization beside the Nile, and Mesopotamia, the early civilization located by Tigris and Euphrates. However, the optimal use and the use of resources more efficiently were not a pressing issue during those periods due to the plentiful resources that more than the need of such a small-sized population. So they were using a very simple technology using surface irrigation. We cannot afford surface irrigation nowadays because population increased, but the water did not. So that's why we've got to think about accurate estimation of crop water requirements and using more efficient system. And we did, over the years, move in the ladder from a low-efficient basin irrigation to furrow to sprinkler to drip. And even we did more in the last decade. We started also to look at lining canals and to avoid the leak and also to avoid losses by evaporation. And in Egypt, there is a huge project, rehabilitation of canals. The government is really pushing into that direction, is to avoid losses by leak. And it's really a very large project. And also here in the UK, we cover reservoirs with floating solar panels. It has two benefits. It reduces evaporation, and number two is to produce electricity for dairy farming, especially those dairy farming to produce a lot of butter, ice cream, and milk, and so on. And so it has double benefit. And the most important thing is also reducing the losses by evaporation. And also here you can also do the lining of the canals to reduce the leak, but as well as you can also cover the open canals of irrigation by solar panels to produce electricity and also to reduce losses by evaporation. And solar pivot is another example that we could use as an efficient irrigation system, and water and energy, 30% could be saved by such irrigation system. Not only this, but also the center pivot system. Now we started to use a low nozzles very close to the ground sprinkler center pivot system to avoid losses by wind drift. And also, if you are using brackish water or treated wastewater, it is important that you have these low level nozzles close to the ground, so you avoid any touch between the farmers with their skin and any pathogens in treated wastewaters, and so on. So technology is moving. Drip irrigation, of course, came to light, but surface irrigation with the drip, you can see here, sometimes it creates some salinity on the surface and also losses by evaporation. So we started now to move to subsurface drip irrigation. That's much better, more efficient. And now the drip irrigation has started to be in use even for rice. And rice is one of the most consuming water in the world, especially in Asia. And here you can see from this experiment in India that the rice yield increased by 40%, water saving by 70%, energy conservation up to 60%, and increased efficiency of water and fertilizers usage up to 80%. So we are moving from the conventional way of growing rice to a drip irrigated rice. More than that, we are actually using partial root drying method. We irrigate half of the root zone of the crop at a time. So we put the plant here and in between two lines of drip irrigation under the surface, 9 to 12 centimeters below the surface, and we put the plant here in between. So the first irrigation, we irrigate the right half of the roots, and the second irrigation, we irrigate the other half. So we irrigate only one half of the root zone at a time, and that saves a lot of water. And we could save here 26% compared to the normal drip irrigation using a PRD, or 44% of the water if we use sprinkler. That's from Water for Crops project as well. So another thing came in the recent few years, the nano irrigation. In theory, nanotechnology and nanoscience is the study of manufacture and handling of structures, mechanisms, and materials on a scale of less than 40 nanometers. A nanometer is 10 to minus 9 of a meter. Nano irrigation is new technology by the way of slowly releasing small amount of water, continuously moistening the soil, enabling 24 hours crop irrigation. The core technology of nano irrigation is moist tube, and the inner layer is a semi-permeable membrane. So this is really how it looks like. And installed under the ground, it is made of semi-permeable membrane with 100,000 nanopores per centimeter square. This releases a continuous small quantity of water near the roots and preventing undesirable effect of percolations and evaporation. The use of this method reduces the repeated human interventions and ensures great efficiency and in terms of cost and optimization of irrigation management for farming operations, agro-industrial companies, and the green spaces, particularly public spaces, tourist areas, lawn gardens, and golf courses, municipalities, and private properties. So this is an example here from Morocco. It is funded by EU projects as well. And here you can see these tubes, and these tubes would seep the water slowly, 24 hours, and irrigates without being touched during the operation. And the nano irrigation amount of water, the amount that can be used to irrigate one tree by surface irrigation, and nano irrigation can be used to irrigate 4. So you can see now how high the efficiency of nano irrigation can go to 95% efficiency if you use nano irrigation system compared to the surface irrigation system. Another type of nano irrigation system is called ULDI, ultra low drip irrigation. And here is the common or traditional drip irrigation. You can see here some water from the drip irrigation goes below the road zone, and that's losses. When you apply ultra low, it means ultra low in pressure and energy and the flow. So the flow is 0.1 to 0.3 liter per hour. The standard or the conventional drip irrigation is between 2 and 4 liter per hour discharge. We are using here 0.1 to 0.3, very low flow, longer period of water release, higher use efficiency, low water retention in the soil, no percolations, excellent water saving, about 30%. And here what you see is the application of ULDI, where the water is kept within the root zone and no losses below the root zone. Another thing came also recently in the next maybe 3 years only, the varying irrigation rate, VRI technology. And that's related to center pivot system, where you don't need to irrigate equally the land under the span of the center pivot system, because you might have light soil, ditch, heavy soil. You don't need to add the same amount of water if under the center pivot system you have that sort of variations. So here you can add more water to the light soil, less water to the clay soil. You don't need to add any water here to the ditch, and you end up by having that sort of mosaic. So you only add the right amount of water to the right place using the GPS or the Global Positioning System, GPS, and Geographic Information System, GIS. And this company now they are. I have seen them recently in Sydney exhibiting this system, and they are really quite impressive to see how this works. And now we have also to consider the energy, and as a part of irrigation needs energy, and also saving water means saving energy. And the new concept now that we are working on in ICID, I'm the chairman of a working group on water, food, energy nexus. And because now the new concept is not more water, more crop per drop, it's more crop per drop per kilowatt, even more than that, per kilowatt and per unit area of land. So we need to take into account the nexus in our work and in our thinking. So in conclusion, water and food security under climate change requires integrated management that includes: 1, estimating accurately the irrigation water requirement, as irrigation consumes 70% of fresh water resources. Population significantly increased, but water did not. Water resources management that accounts for the impact of climate change, increasing water supply to narrow the gap between water supply and the demand, encouraging the use of non-conventional water resources under suitable management, enhancing water use efficiency, reducing losses, using nano irrigation, using VRI, PRD, automation, encouraging the use of non-water consuming crops, non-conventional crops, encouraging the use of precision agriculture and precision irrigation, encouraging the use of models as management tools, and develop mobile apps friendly and easy to use by farmers. Encourage the biotechnology and its application for food security, enhancing land management, mixed cropping, companion crops, conservation tillage, agro environment, wildlife strip to increase pollination and yield. New technologies and innovations can help in water saving, as we need to count every drop, because every drop counts. Thank you.
Thank you so much, Professor Rajab, for this amazing presentation. Actually, it has a lot of information and the new information, at least for me. Thank you so much.
You're welcome.
Rania, could you enable raising hand button for the audience?
Okay.
Because better to listen to the people, our colleagues. We have some, until you do this, we have some questions in the Q and answer box. So, Professor Rajab, shall we start with this question, or you allow the people to speak?
Well, I think I allow them to speak.
Okay.
Yeah, I'll allow everyone to speak.
Okay. Said, please start your questions.
He's muted. He is muted.
Mr. Said Niazi,
He is muted.
we don't have a lot of time to lose, so
I wonder if you can hear me.
Yeah.
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 It's very
Hello.
nice to see you, and it was very nice presentation. I would like to say only one question I have in my mind all the time. What technique, any technique which we use to increase the yield, that means that we are consuming more water. So I'm very concerned about new technology to increase the crop production. That means that we are evaporating, transpiring water more. So in fact, using high technology, it is really increasing productivity. However, consuming more water. So I have to, I'm concerned about the water resources management as a whole. That is my question.
Okay. Thank you, Said. Well, the new technology actually aims at reducing the amount of water that we apply. So that's the main idea. And the Water for Crops project that we saved about 26% water when we compare the drip with sprinkler, and also no, it was 44% saving when we compare the PRD, or partial root drying method, with a sprinkler, and also we saved 22% of water when we compared the partial root drying method PRD compared to regulated drip irrigation. So we are actually moving towards not using much water for irrigation. But when it comes to the yield, the increase of the yield is not only based on water, based also on land management and biotechnology. For example, that we here in the UK, the Ministry of Agriculture and Fisheries, they encourage farmers to have a companion crop and to have a different crops growing in strips on the field. And the reason for that is that they encourage the pollination of the main crop, and encouraging the pollination would increase the yield. So that's one example that we not focusing only on water, but also on the land management. So it's a combination of biotechnology, that you can have a variety that's more yielding than the others, and also you can have the water management in addition to the land management. it's integrated really management. That's what we are looking at. Any other question?
Good evening.
Can I ask a question?
Yes, go ahead.
Excuse
Yes,
me. You
yes.
heard me?
Thank you, Prof. Rajab, for this informative presentation. I am Naeem Mazahri from Jordan, and I am one researcher who is working in the Eddy Covariance in the Jordan Valley. We found underestimated value also with the weighing gasometer behind. This is maybe for the footprint, maybe. We need large to get more accurate information. My question about the cosmic ray. Now I am using the cosmic ray in the Jordan Valley for date palm trees. And you know, it is spot not all full field wetted. Only we have spots with between trees and dry and wet around the trees. How we can calibrate this? I am facing a problem in calibration of cosmic ray in that way, because we have dry spots and wet spots, and I collected data, but I faced a problem in calibration of the cosmic ray. Thank you.
Yeah, I think the calibration of the Cosmos values, when you have really a wet and the dry areas, will be quite difficult, because the Cosmos gives you an average value that combines both. But what I would do is maybe I will try to find a correction factor that relates to the relative area of the dry compared to the wet, and I think I would take that into account when I adjust the Cosmos soil moisture. So if I were you, I would make an estimate of the dry area compared to the wet areas, and I'll try to find a way that I can correct that and compare it. So if I can derive a factor, I will still test that factor to see if that actually brings me to the correct value of the wetted area. That's what I would do.
Thank you, Dr. Ragab, for the presentation. My name is Ahmed Hashim. I'm an assistant professor in Suez Canal University in Egypt. And I'm wondering if you have considered using the ASCE standardized reference equation that was like improved FAO 1998 for the comparison with your results.
No, the simple answer is no. We only used the 1998 that maybe came later than the equation that you mentioned now, and that's the equation came as FAO irrigation and drainage report number 56, which is a product of cooperation between ICID and FAO. And because of the wide use of that equation all over the world, we only focused on that equation.
Thank you, Dr. Ragab.
Professor Abdul Rasul Al-Omran.
Yes, thank you, Professor Rajab. I do have
quite a few questions I would like to ask. One of them is, can you in general say that, or presume, can you say that using the EC or to estimate crop water requirement, can it be possible that ETO or ET potential, 40% of that will be equal to the EC measurements or EC estimate in general, between 30 to 40%, so we can, and at least not using that term of deficit irrigation.
Well, our really measurements indicated that 45% is related to the amount calculated by FAO 56, not related to any other method. So it is only associated with that one. So if anyone is using FAO 56, that should know that it is overestimating the crop water requirement by almost double. But if you are using different methods, we didn't really try other methods. But
well, it's the same. I'm using the same method to estimate the potential ETO or the ET or the ETO. But my other concern, as you know, most of our soils are sandy soils.
Yeah.
In your work on Eddy Covariance, have you engaged in such a work of using the soil texture too, or this is only related to the efficiency of the soil whole systems?
The soil that we use in Water for Crops site, as I mentioned in my presentation, it is actually silt with fine sand. So it has a lot of sand and silt. So it's very light texture soil. And sometimes, of course, we feel that it is different from the clay soils where the soil moisture stays maybe closer to the surface compared to the sandy soils where the water goes a bit deeper. And also the root zone, the roots, they are maybe shallower in heavy clay soils compared to the sandy soils because they have to go down and to search for more water. But yeah, we tried light textured soils, but we didn't really compare that soil with other soil types. We didn't really go into that sort of comparison, but it will be, yeah, something interesting to try in different maybe research or projects.
Good evening. Do you hear me, please? Yeah, good evening. Hello. Hello. Hello.
Dr. Lami Ahmed, Hamid.
Yeah, do you hear me, please?
Yeah, I do hear you.
Okay, good evening, Dr. Ragab. This is Lami Hamid. I'm associate professor at Soil and Water Department, Cairo University. Recently, I'm associate professor at King Faisal University. Actually, thank you so much for your impressive your presentation and your topic. Really, it's very interesting. But I have just a concern about the system that use ultra low drip irrigation. Is it applicable for all the regions? I mean, with high temperature like Gulf countries. As I know or I understand from the presentation, this is a very few future content around the zone or root zone, but I'm continuous one. I'm right? Is it? How the evaporation comes from this soil? Also, you talked about the nexus of crop per drop and also energy, along with the unit per land. How the energy consumption during the using this system, which is ultra low drip irrigation, and if it's applicable for all type of soils or not. Thank you so much.
Well, thank you. I think the ultra-low drip irrigation, you can see from the slide, the range is 0.1 to 0.3. And the reason for that, it depends on the soil texture and type that you can either use the slow. If it's a light texture, you will have to use the slow to avoid deep percolation. And actually, it's better to have it as subsurface to avoid surface evapotranspiration and any losses from the surface, from the soil surface, can be avoided if you put the tape or the tube, say about 10 centimeter below the surface. And at the same time, if you have a light texture soil, then you can use a slower rate, lower rate. The slide that I showed about the lady in Morocco using the nano irrigation system, it is very light texture soil of orchards, and it seems to work for the ultra low drip irrigation. Really, it is very low, and you save on energy because you don't really need the same energy, the one that you apply for the normal drip irrigation. So for ultra low drip irrigation, it is low in pressure, as they say, and low in energy by definition. So you are, when it comes to Nexus, then you will be saving on the energy and on the water, both of them. And that's really in the essence of the Nexus.
Thank you very much. Professor Anwar. Professor Anwar Ali. Mr. Magdi Sayed. Okay, Omar. Start your question, Omar.
Okay, so Omar Ali, I'm a researcher at Southampton University. Actually, this is a very interesting presentation, and I have got one interesting point. Actually, Professor Ragab highlighted that he can't or he couldn't use the remote sensing data within the work he used for retrieving the soil moisture content. Actually, as far as I know, that soil moisture content can be retrieved over the topsoil of the over the topsoil only for 5 centimeter or 10 centimeter. So my question raises actually, what kind of methods do you apply remote sensing data to come with this conclusion? This is the first thing. Second thing, actually, when you compare remote sensing data or the retrievals from remote sensing data of soil moisture with the CR exactly, you have a radius of 700 meters, almost of the CR. So the amount of water you get from the CR method, is it a bulk amount over the 60 centimeter depth, or it's only you can produce a map from this instrument? Thank you.
Well, my work in the remote sensing is that if you look at the images that we obtain, you never get a direct measurements of soil moisture by remote sensing. So basically, you measure dielectric constant, scattering coefficients, and brightness, temperature, and then you go through a lot of transformation before you come to soil moisture. And that's my experience. The other experience I got is that you sense the soil moisture of the top 10 centimeter or so. I've been working with the C band and later the L band, and using the active microwaves. You never really get actual and direct measurements of soil moisture. And the calibration here becomes difficult. And the other difficulties that we faced is that how can you apply that for agriculture? How can you obtain the soil moisture of the root zone from the surface layer soil moisture? And when I started to work on that, I developed a model published in Journal of Hydrology. It's called the 2 layers model. where from the soil moisture of the top layer obtained by the remote sensing, I could calculate the soil moisture of the meter, the first top meter of the soil. And that was the way to do it, because simply most of these remote sensing, they never go deep enough, while the Cosmos can go up to 60 centimeters, and some literature, as I presented, they say that it goes even to below 80 centimeters. So you cannot really compare like with like. So the Cosmos here might not be really suitable for that remote sensing, and I would look for maybe another way of calibrating the images of the remote sensing.
Dr. Anwar.
Hello? Hello?
Dr. Anwar. Hello, please
Yes.
start. Please
Yes,
start.
yes. Yeah, thanks, Prof. Ragab, for this interesting and up-to-date innovative lecture. I'm wondering if you can help us to initiate a Cosmos station here in Egypt with the support of Center of Excellence. Is it applicable or not?
Well, everything is possible, but yeah, we need to get someone to sponsor or to fund that research, really. So if we can find someone who would support
How much it will cost?
financially that
How much?
initiative, we are quite happy to yeah, to do that.
Yeah.
How much is the fund, Dr. Ragab, to do this?
Sorry?
How much?
How much cost?
No, the cost is not really the instrument. The instrument is not really the real cost. It's the installation, the training, and also you need automatic weather station to go with it, because I didn't really go into details. We have to do corrections for the air pressure, relative humidity, and other meteorological parameters.
What is approximate budget for all this?
Yeah,
approximately, not roughly.
I have to work that out, not in second. No, I have to work that out.
Okay, if possible, maybe the Center of Excellence for Agriculture and Water will be interested in this. So maybe if you have time, just give us a rough estimation. It will be
well,
much.
they have my email, and get in touch with email.
Okay.
So I can give myself the right time, and I ask about the real cost now.
Okay, thank you so much.
Cost changes by time as well.
Of course, of course. Thank you, Dr. Anwar, for this very interesting and challenges question. Magdi Sayed, Master Magdi Sayed, we have Magdi Sayed and Ala Masood. Then we'll request you to quickly answer the Q&A question, if any, briefly. Please start.
Yes. Can you hear me?
Yes, please.
Yeah, thank you, Professor Ragab, for comprehensive and interesting presentation. I really appreciate this effort and this interesting presentation. Thank you, Dr. Abazim, also for managing this interesting gathering with Dr. Ragab. Dr. Ragab, you presented several methodology for measuring water requirement. You know, in Egypt, sometimes we don't have fund for Cosmos or some expensive machine, and especially we have facing now some economic problem. What do you think the best? I mean, based on Egyptian condition now, the best method for calculating water requirements? Yes, in new area, in desert area, and in old land, in the old land and the new land. Yeah, thank you so much.
It's really quite a tricky questions, because you cannot say the best method for Egypt is this one or that one. So it's really a matter of the affordability. What method I can afford in the new reclaimed areas. As I mentioned before, if you cannot really afford Eddy Covariance and Scintillometer or Cosmos, then you have to find a way. You can do field measurements. You can take soil cores, for example. You can do a non-weighing lysimeters, POTS, for example, and you try to find a relationship between what really you measure by simple methods, like non-weighing lysimeters, like soil cores and so on, with an easy and calibrated empirical equation, and try to find the relation between these two, and then you use that equation after being modified for that site. I have seen some people, they use equation of Hargreaves. And this equation, why it's used in so many poor countries, it is only based on temperature. And temperature is something anyone can find. So they use that equation, but some of them, they don't really calibrate the equation. And they fall into that trap of errors. But I think if really you have a limitation or not much resources, I would go for a simple empirical equation, and then I can try to test this equation with some few but long-term measurements in the field, and then I use that equation for calculating the crop water requirements. That's what I would do if I have nothing else really to afford to get new technologies.
Okay. Thank you so much. The last one is Ala Mosad. This is the last attendees raising his hand. Then we'll go quickly to the question and answer. Bottom, please, just if you can briefly answer them. I responded to many, but still some questions are there. Ala.
Is muted.
Ramadan.
The microphone is muted.
Oh, Ramadan. Okay. Ala.
Hello?
Please quickly, because we are running out of time. We still have 2 minutes.
Yeah, can you hear me, please?
Yes, please continue.
Yes, I am Ala Musad, researcher at the Agricultural Research Center of Egypt. I wanted to ask Dr. Ragab about the actual cost of the systems he mentioned, whether Scintillometer or Eddy Covariance or the Cosmos system. Just a question about this.
The cost, I cannot send them to you by email after I check, because the cost changed since the project. So I don't really have to to give you a cost now, and then you discover it has been doubled. So I need to double check the cost of the equipments. But also I also would like to tell you that some suppliers and countries, they have different rates. So when you buy equipment from Egypt, it might be cheaper than buying it from USA, for example. So the local suppliers, they have different rates, but I can send you some information about the manufacturers and the exact trade name, so you can maybe check on the cost by direct contact to manufacturers.
Mr. Ala, please send your email via chat. Then I will send it to Professor Rajab to communicate with us about this.
Okay, I will do. Thank you all.
Please.
Thank you.
Yes, now. Professor Rajab, may you please kindly check quickly a Q&A button? Still we have a few minutes, if possible.
I think there was a question from Dr. Abdul Rasul, Professor Abdul Rasul. I answered that one.
Okay.
The first question, thank you for research. I haven't considered ASE standard. This also answered. Number 2.
Okay.
Also, number 3 answered.
Mm.
From Dr. Hussein, Vice President of ICID. Thank you very much for your informative expressions. Do you advise if take into account 30 to 40% less water from Penman-Monteith calculated one if we do not have Eddy Covariance or Scintillometer? The answer to this question is that I could try to reduce it by 30 and 40% and on experimental plot and then see what the results are. Yes, I would try that, but on a small plot. Can we still keep safe site and apply irrigation based on calculation Penman-Monteith? The answer is no. Penman-Monteith modified version. I'm talking about the modified version that needs to be reconsidered and to be checked. I wouldn't apply Penman-Monteith modified equation as in its current form, and I should check that with experimental plot. Back to Beck. It is great to see you, Dr. Ragab. My question is this: technology measure ATA or ATC? The Eddy Covariance and Scintillometry, they measure only ATA. So if you want to have I don't see why you need ATC, because the beauty of using Eddy Covariance and the Scintillometer is that you don't need to use the KC to multiply it by ET naught to obtain the ATC. So you don't really need to look for ATC, or you look for KC. So what actually comes from the Scintillometry and from Eddy Covariance is the actual evapotranspiration, and it is the exact amount that you should add for irrigation. Another question here. Thank you for the valuable, informative presentation. Which method are recommended by FAO for calculations AT along this new technology? Question 2. Most of the new technologies are not available in Arab and arid region. So how to convert these technologies to our region? The technologies are available and they are used even in Morocco and in Jordan. So the technology is available, used in Morocco, used in Jordan. I give examples of the using of Eddy Covariance in Jordan, and also in Egypt. I have colleagues, they are using it in Egypt. So the technology is there. As for the best recommended FAO calculation of AT, I don't recommend the current modified Penman-Monteith equation without being checked in the field with real measurements and work out what would be the correction factor. What does nano irrigation mean? I explained that, I think, in the slide.
You can see the presentation on it. It will be in the website.
Yeah, I think it is explained that it is perforated tubes with very small pores, with 100,000 pores per 1 centimeter square. And the inner part of the tube is a semi-permeable membrane, and that would release water slowly and continuously to the root zone. That's the answer. I need to ask a question. Yeah, that's already answered. Magdi Sayed. I answered that. Yes, low energy and the low flow at emitter, but what about the minimum energy required for filtration? The minimum energy required for filtration depends on the quality of the water. So if really you have a clean water, then there is no much energy really needed to push the water through the filters, and the resistance will be less. But yeah, it is at least you can save on the pressure of the water going into the drip lines, at least. Thank you, the team. Very informative meeting. Another question. you mentioned the Penman equation gave higher ET results in comparison to other methods. So in terms of deficit irrigation calculation, is the results obtained by Penman not a deficit irrigation? And given the results of other researchers, not only me, who they declared that the Penman-Monteith equation, modified equation of FAO, produced higher values, then you cannot really use that equation and call the amount deficit irrigation. So deficit irrigation has to be properly calculated based on the actual irrigation requirement. You have to know first what's the actual requirement, and then a percentage of the actual is the deficit. And that's the definition of the deficit. Deficit irrigation is a ratio of the actual, but not the potential. What you calculate from the equation is the potential requirement. So that's the answer to your question. Hani Mahanna, thanks for your informative presentation. How could we enhance our role as researchers to raise the Egyptian public awareness? Media is one thing that's very important, the media. Mobile apps, I refer to that. Mobile apps are very important, that farmers and the users, they should have information about the amount of water they should irrigate. And there is now a mobile app developed in USA, where farmers, they can, while they are in the tractor driving, they can see the need for irrigation and how much it should apply, and so on. So there are now mobile apps that are very friendly to use by farmers. It gives them really the real. And also there is one here in the UK about soils. It's a mobile app about soils that you can walk around with the mobile app, and then you can look at the site, and then it will give you some information about the salinity, the pH of the soil, the texture of the soil, the nutrient status. So mobile apps has a future to play, not only for farmers, but also for researchers. And that would raise the awareness. What's the name of the model you developed to get soil moisture in 1 meter from remote sensing data? You need to look for Journal of Hydrology. The model is called 2 layers model, and it is published in Journal of Hydrology in 1995. You can get in touch with me. I can give you the full reference if you wish. It's the Journal of Hydrology. You can go to Journal of Hydrology website. You can either put my name or look for the year 1995, and you will find that paper.
Thank you so much, Professor Rajab, for this truly amazing and informative presentation. We are so happy for this. This is the first webinar that a lot of questions directed to the presenter. So this means our topic is very important, and the technologies gets attention of the people. So thank you so much. Please, colleagues, the papers are in the chat box. You can download before we close the webinar, because we are half an hour almost out of the time. Thank you for your patience, Dr. Rajab.
Yes, you're welcome. You're welcome.
This is we expected this from figures like you, and we hope that we can host another webinar and another interesting topic, particularly misconception and misunderstanding of the water management. We will get the paper, but maybe in the future we can invite you to deliver another presentation. Still, the project is extending up to 2000. 28. Maybe we can meet again if you can allow us to give us more time. Thank you so much, and I think now we can close.
Maybe you need to allow people to copy the papers, maybe.
Yes. Ecology, thank you so much, Ecology. Thank you, Rania. Thank you, Dalia,
Thank you,
for
Dr.
staying
Ablas,
with
and
us
thank you,
all
Dr.
this
Ragab.
time. I know that it is late for both of you, but the topic is, as you see, is so important, and again, the interest of the colleges. This is because actually we need to implement one of these technologies, or maybe in Egypt, so the people are interested not only in Egypt but also other countries. So please, some people, some colleagues asked for the presentation. Can you please send the PDF to me or not possible?
I thought you are recording it, no?
It is recorded. So Rania, when you will upload the webinar on the website, can you send us the link or share
Yes,
the
sure.
link with the presenter, with me, and with the attendees, if Professor Rajab allows?
Okay.
Yeah. I also would like to put a copy of the recorded presentation on ICID website.
Okay, please send us the link, and send also the link to the attendees whenever it is available for you. You have always the emails of all the people, and whenever you prepare the statistics and the report of the webinar, please share it with me and with Professor Rajab.
Okay, Doctor.
He needs to know how many from where and from which organization, because maybe the people will contact him and he could be answered to. Thank you so much for all of you. Again, thank you, Professor Rajab, and thank you also for Professor Anwar Ali, because he was the one who nominated Professor Rajab for this webinar, and I catch the idea and contacted him, and he kindly agreed to deliver this webinar. Thank you for all of you, and it was actually a very nice time to see all of you and attend this webinar. Bye-bye.
Bye-bye. Thank you.
Thank you so much. Bye-bye.
Thank you. Bye-bye.